In this presentation, I'm going to talk performance of components reducing their isentropic efficiency. I choose types of turbine performance to decrease with us, thus reducing their isentropic efficiency. What is turbine? Turbine is a mechanical device that extracts energy from a fluid, such as a gas, steam, or water, and convert it into rotational mechanical energy. It consists of blades or vents mounted on a rotor, which is connected to a shaft. When the fluid flows over or through the blades, it imparts a force that causes the rotor to rotate. The rotational of the rotor can then be harnessed to drive various types of machinery such as generator, compressor, and propeller. Turbines are used in a wide range of applications including power generation, aircraft, propulsion, hydroelectric plants, steam-driven machinery, gas compression system, and more. Gas turbines, steam turbines, and water turbines are some common types of turbines used in different industries. Question 1. How does the component function? So, how does gas turbine function? A gas turbine is an engine that converts energy from burning fuel into mechanical energy. It is commonly used in power plants and aircraft propulsion system. Here is an overview of how gas turbine work. This process begins with the intake of atmospheric air, which is compressed and direct into the combustion chamber. Air is compressed by this compressor, usually consisting of multiple stages of rotating blades. The compressor raises the air pressure, allowing for efficient combustion. The combustion fuel that is usually used in natural gas, oil, or liquid fuel injected into the combustion chamber together with compressed air. The mixture is ignited to produce a high temperature, high pressure gas. The hot gases resulting from combustion expand and pass through a series of turbine blades. The energy of the gas is transferred to the turbine blades, causing them to rotate. The rotating turbine shaft is connected to generator, which convert the mechanical energy of the rotating shaft into electrical energy. After passing through the turbine, the exhaust gas is discharged into the atmosphere, usually through a chimney or exhaust duct. Question 2. What measurements are typically recorded during the operation? During the operation of turbines, various measurements are recorded to monitor and control their performance. The specific measurement can vary depending on the type of turbine and its application. Here are some common measurements recorded during the operation of gas turbines, which is efficiency and performance parameter, power output, pressure, temperature, flow rate, and vibration. For measurement efficiency parameters, various parameters are measured to assess the efficiency of the gas turbine. This may include isentropic efficiency, polytropic efficiency, overall efficiency, and specific fuel consumption (SFC), which measure the fuel consumption per unit of power output. For next measurement is emission. Gas turbines produce exhaust gases, and measuring emission is essential for environmental compliance. Emission measurement commonly include levels of pollutants such as nitrogen oxides, carbon monoxides, and unburned hydrocarbon. For the last measurement is flow rate. The flow rate of the fluid through the turbine is an important parameter to measure. It indicates the volume or mass of fluid passing through the system per unit of time. Flow rate can be measured using various techniques such as flow meters and is typically recorded in units such as liters per second, cubic meter per hour, or kilogram per second. Gas flow rates at different stages of the gas turbine, including air intake, fuel flow, and exhaust gas flow, are recorded to monitor and control the turbine's operation. Accurate flow measurements are crucial for maintaining the turbine's efficiency and power. Question 3. Causes of degraded performance with the use of turbines. The performance of turbines can degrade over time due to various factors. Here are some common causes of degraded performance with the use of turbines. For the first causes is volume and deposit. Turbine component, particularly the blades, can accumulate, deposit, and falling over time. This can include dirt, dust, mineral deposit, and other contaminants present in the fluids. Falling restrict the flow of the fluid reduces the effectiveness of the blades and diminishes turbine performance. Over time, gas turbines can accumulate deposit and falling on various components such as compressor blades, turbine nozzles, and heat exchanger. This deposit can restrict airflow, reduce heat transfer efficiency, and degrade performance. For the second causes is erosion. Turbine blades can experience erosion due to the impact of solid particles suspended in the fluid flow. This erosion can gradually degrade the aerodynamic shape of the blades, leading to reduced efficiency and performance. High velocity fluid flows containing solid particles can cause erosion of gas turbines components. These particles can impact the surface of compressor blades, turbine blades, nozzles, and other critical parts, leading to material loss, reduced aerodynamic efficiency, and decreased turbine performance. For the next causes is corrosion. Turbines operating in corrosive environments, such as those using seawater or high temperature gases, are susceptible to corrosion. Corrosion can damage turbine components, including blades, casing, and piping, leading to performance deterioration and potential structural integrity issues. Chemical reaction between the working fluid and turbine material can result in corrosion. Corrosion can occur due to the contaminants, impurities, or the operating environment. Corrosive agents can attack turbine components, leading to material degradation, loss of surface integrity, and reduced performance. For the last causes is control system issues. Turbine performance can be impacted by malfunctions or inaccuracies in the control system. The control system plays a critical role in monitoring and regulating the operation of the gas turbine. Malfunctions, inaccuracies, or failure in the control system can lead to suboptimal performance. Issues such as improper fuel air ratio, inadequate temperature control, or faulty load management can result in decreased efficiency, increased emission, and overall degraded turbine performance. Question 4. Maintenance action that can be taken to extend the service life of turbines. To extend the service life of turbines, various maintenance actions that can be taken. Here are some key actions that can help in prolonging the lifespan of turbines. Regular inspection. Conduct regular inspection of the turbines to identify any sign of wear, damage, or potential issues. Inspections can help in the early detection of problems and prompt repairs. For the second maintenance action is lubrication. Proper lubrication is essential for the smooth operation of turbine components. Follow the manufacturer's guideline for lubrication and ensure proper lubrication of bearings, gears, and other moving parts. Use high-quality lubricants and adhere to recommended lubrication intervals to reduce friction, wear, and extend component life. For the next maintenance is cleaning. Regularly clean the gas turbine components to remove deposit, falling, and contaminants. Clean compressor blades, inlet filters, heat exchanger, and combustion system to maintain optimal airflow, heat transfer efficiency, and combustion performance. For the last maintenance action is performance monitoring. Utilize condition monitoring techniques such as temperature monitoring, oil analysis, and acoustic monitoring to access the head of turbine component and detect any sign of deterioration or malfunction. Implement a comprehensive performance monitoring program to track key parameters such as temperature, pressure, flow rate, efficiency, and emission. Analyze performance trends, deviation, and alarms to identify potential issues and optimize gas turbine operation. Also, to access the head of turbine component and detect any sign of deterioration or malfunction. For conclusion, in summary, we can analyze thermodynamic phenomena in gas turbine, provide valuable insight into factors affecting isentropic efficiency, and guides effort toward design optimization, operating condition optimization, heat recovery, emission reduction, material investment, and effective maintenance strategies. Manufacturers can make informed decisions to enhance gas turbine efficiency and tailor their industrial application for specific needs. This can result in improved performance, reduced operation costs, and a more sustainable use of gas turbines in various industries.